piggybacking off of u substitution is something called a trig substitution. And you'll find that when you're dealing with trig functions, that there's often an identity that you can swap out before you do your trig substitution. So this would precede a u substitution, and it would lead to something being very simple. So I'm going to show you a couple, but we probably should review some of our common trig identities, okay, that you'll need to know. Most of the ones that you need are listed. I think all the ones you need are listed in the book, but we'll just review a couple. Give me one you remember. Okay, the Pythagorean identity, right? And that comes in many different forms, right? So sine squared plus cosine squared is 1. So that can come in a couple different iterations, right? You could also say, well then, sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared. Oops. But it also has iterations that involve cosecant and tangent and secant and cosine, right? So you've got the different variations on that. So there's another one that says that tangent squared plus 1 equals secant squared, and you have the variations on that where you can have it look like subtraction or move those different things around. There's also cotangent squared plus 1 equals cosecant squared. So again, you just have the different varieties of that. Okay, you also, those are the Pythagorean identities. That's one we're going to talk about, yep. Okay. So then you've got a few other trig identities. You've got cos 2x, which is 1 minus 2 sine squared. That can be proven with the cheer. And so then that's called the double angle identity. And so you can like modify that and again, like move it, have the 1 be on the other side and move different things around. Any of the other ones, I think you're going to know they give you as a quote-unquote hint in the problem. It'll say like, hint, go back to number 45 and look at the identity there, or like, hint, use this one. So I think you're going to pretty much have everything that you need. Okay? I think you're thinking the law of sines, maybe, the law of cosines. And we're not going to need those. Okay, so here's a couple to try. Okay, so integrating something like cosine cubed of x, which, again, I was talking to Justine about thinking of that in terms of parentheses. So it would be cosine of x within the parentheses of cubed dx. So traditional u substitution doesn't work here, because according to the traditional rules of u substitution, what would you choose as your u? Yeah, you'd choose cosine of x, but what's the problem in choosing your u as your cosine x? There's no sine of x that's going to reduce away, right? And so traditional u substitution doesn't work here. And so we're going to need to do some trig substitution first. So then you need to think of this in terms of cosine x squared followed by a single cosine of x. So those are the same thing, right? That's the equivalent. You're just grouping it differently. You're making this into a product. Because once it's a product, then traditional u substitution will work. Okay, so cosine squared, that is one of those trig identities. Okay, so it's 1 minus sine squared. And then cosine of x dx. So we're doing a trig substitution here, and now we'll do a u substitution. So trig substitution just precedes u. So seeing what you have in terms of your product here, and knowing that it's multiplying by cosine, what would be a good choice for you so that what you choose intentionally will reduce out what's left in the other side of the product? What do you think? Just the sine part. You don't have to do the 1 minus sine squared part. Just the sine part would be a good choice for your u. And so then your differential on u would be the cosine of x dx. And so dx would be du divided by cosine of x. So then I'm ready to do my u substitution, which will become 1 minus u squared. The cosine, as part of the product, still is there, but the du part is going to take care of that. And so I'm left with 1 minus u squared. And we can do the antiderivative of that without too much problem. So it was a trig substitution that preceded the u substitution. So I'm looking at u minus a third of u cubed plus c. And then you'll replace u with the original choice that you made. So it will be sine of x minus 1/3 of sine cubed of x plus c. Do you ever stop to think like, like that's what I got for the antiderivative, and if I check it, it'll just simplify back down to what simple derivative? Like what did I start with? I started with cosine cubed. So the derivative of this thing works out to be cosine cubed. You could check your work. It works out. You need an identity when you check your work again. You take the derivative and then do an identity. But yeah, it works out. Okay. All right, so let's try another one. Bless you. Okay, so the integral of 2 sine squared x dx. Okay, again, if I think of this in the traditional sense, so 2 parentheses, sine of x quantity squared dx, if I think about it that way, u substitution isn't going to help me, because traditionally I'd pick sine x as my u, but there's no cosine x there, so again I'm running into the problem of not being able to reduce. And so I'm going to need a trig identity again. So 2 sine squared is going to come back to, and I'll scroll up, this second identity right here. There's 2 sine squared right there. If I isolate 2 sine squared, I've got the identity 2 sine squared equals 1 minus cosine of 2x. And so then I'm going to replace and do a direct u substitution of 1 minus cosine 2x. Excuse me. And I don't even need any other substitution. I can directly do the antiderivative as it is.
You don't even need u.
I don't need u. Because what's the antiderivative of 1? Okay, what's the antiderivative of negative cosine? Negative sine, okay, of 2x. But I do need to remember the to divide by 2. And then plus c. So I didn't need a u. Now you could do a u substitution if you wanted. The only u would have been what's the 2x. That would have been the only thing. All right, so part of your homework is going to be that kind of thing. And a lot of times they'll give you a hint about what the trig substitution is supposed to be. The second half of your homework is going to be a set of proofs. And we use trig substitution to prove the inverse trig derivatives and antiderivatives. Okay. The other thing that trig substitution is good for is we use them to prove the inverse trig integrals. And that's this sort of, so your homework's kind of like in two themes, two chunks. It's u and trig at the same time, yeah. So trig and u substitution, I guess, using both kind. Okay, so let me show you what I mean. Okay, if I gave you the antiderivative of negative 1 over the square root of 1 minus x squared dx, I think by memory, you know what the answer of that is going to be. At least I hope. Close. Inverse cosine, okay? We know that the answer to this should be the inverse cosine of x plus c. You only know that because at one point I told you that's what it was, and you've memorized it. Okay? At that point, you didn't know enough about integrals yet to be able to understand a proof, but now you do. So let me show you how the proof works. How do you fill in the gaps to know that's actually how it works out? And it's with a u/trig substitution. Okay, here's what we start with. So the proof starts with a u substitution of the cosine inverse of x. I make that choice based on what I know the answer is supposed to turn out to be, and I'm going to show it by choosing the appropriate u. If that's the appropriate u, you want to rewrite that so that x is alone instead of u being alone. What would that look like if x was by itself? X equals regular cosine of u. And then what would dx look like? Negative sine u du. So I choose an appropriate u, I isolate the opposite variable, and I find my differential. Now I'm going to do the substitution into the integral. So the integral will become negative 1 over the square root of 1 minus, okay, 1 minus what? So I want 1 minus x squared. 1 minus cosine squared, u. Times dx, which is replaced with negative sine u du. The first thing that happens is I have a double negative. So that will give me a numerator that's sine u du. That's the first thing that happens. The second thing that happens is the trig identity in the denominator, which we have 1 minus cosine squared, which is sine squared. Now I have the square root of something squared. Okay, yeah, so I get the sine of u du divided by the sine of u, which reduces. And I'm left with simply du. And what's the antiderivative of du? U plus c. And what did u represent? U was the inverse cosine of x. And so now you've proven that it turned out the way you had memorized it to turn out, but now you see why. It's just that at the time, you didn't know enough to to be able to understand that, but now you do. So sometimes you got to take stuff on faith until you actually know enough of the math to be able to understand a proof. I want to do one more of those. We're going to prove one more of them, because there are 6 inverse trig ones. I'm going to prove 2 of them for you. Some of the rest are left for you to do in your homework. All right, so our final example. We're going to prove that the integral in the form of -1 over 1 plus x squared dx turns out to be, okay, so by memory, what do you know that to be? Okay, it is, oops, inverse, it's not negative, but it's inverse cotangent of x plus c. All right, in the same model, we're going to start with our choice for u. We are going to choose u to be the thing that we know this is supposed to turn out to be. So u will be chosen to be the inverse cotangent of x. So then we'll isolate that so that x is by itself. So x is equal to the regular cotangent of u. And then we find the differential on that. So dx is the negative cosecant squared of u du. Then we do our substitution. So I'll have -1 over 1 plus cotangent squared of x, of u, thank you. And then times dx is negative cosecant squared of u du. And so we see a similar thing happen here, is that the negatives work together to make cosecant squared u du in the numerator. And the denominator is another identity. And that's one of those Pythagorean identities, which is the cosecant squared of u. And so we have a real clean reducing where we just get du. Antiderivative again is u plus c. U was chosen to be the inverse cotangent of x plus c. And there's the complete proof. So they're real similar. It's all in the choice that you make for u at the beginning.